calculate one end of the confidence interval, right? So that was something like, so that's estimate for the population proportion. So we have a sample proportion, subtract z-square multiplied by pq over n. Of course, p and q are both with a hat because that's coming from sample. And then the other side is the same exact expression, but with a positive sign. So I did the other side and asked you to take a look at the proportion on the left side. So P with a hat, I believe it was problem 31, was 0.032. It's a complement, which is 1 minus P, happened to be equal to 0.968, right? And then we also had sample of size 221. And then we also use the confidence level of 99% that gave us Z, the favorite 2575, right? So we have to replace all of that into the left end for the formula. So we put 0.032, subtract 2.575, and then multiply this by the square root with 0.32 in numerator, which is also timed by 0.968, right? And then divided by sample size, which is 221. So that's the left end of that confidence interval. So let me use the calculator and get the result. So scientific calculator, the favorite. So we take this Desmos tool and get 0.32, subtract 2.575 multiplied by the square root extracted from 0.032. So that was a pure calculator exercise for your practice. And if you did not get it correctly, well, do it again, because it's really same exact thing from one side to the other side. In fact, I can really quickly to get the other side of this interval just to show you the usage of calculator where I have to change my minus sign with a plus sign, right? So you can just highlight this and reinsert positive, and that's what I had for the other side of this interval, which is a 0.062. And of course, the main question is, does this really make any sense for that particular exercise? So let's see what happens. 3% of people experience dizziness. 3% in that sample. So what's the percent of people in the entire population that would experience dizziness? So it turns out about 6%, the worst case scenario, maybe less, maybe pretty much 0%, that's the left end, but we'll always go with the worst case scenario, and that's actually the largest percentage of people that experience dizziness. So please notice that this is percentage. It's always in between of 0 and 1, because that's probability, cannot exceed 1. So if your answer for a percentage happens to be more than 1, well, then something is miscalculated. And that's something that one should realize. So that was part A of the exercise. I constructed confidence interval. So somewhere on this interval in between pretty much 0 and 6 something percent is proportion of people that experience dizziness. For the part B, they say in the same test, people got a placebo and 1.8% of those people reported dizziness. Well, dizziness reported again 1.8% or 0.018. So they didn't get a drug, but they were still dizzy. Okay, so based on this result from part A, what can we conclude about dizziness as a adverse reaction? So is it really making sense that dizziness is an adverse reaction if 2% of people experience dizziness anyways? Well, probably, who knows, it's 6%, the worst case scenario, so maybe it's still possible that it does give people dizziness, because it looks like it's possible that instead of 2%, 6% of people get dizzy. So it looks like it doesn't really tell us much in here. So we working with the formula that deals with a confidence interval. Remember, last time we also worked with so-called sample size formula that we wanted to get for the I guess approximation population mean. So it was z squared sigma squared divided by a square of error. Remember, we had that formula for finding the sample size to start studying, and that was in the section 6.3. So analogously, in the section 6.2, the one that we are dealing with, we can also find the sample size if we call that as error. In other words, if I go into isolate in here by taking this whole thing squared, so you got a z squared multiplied by p and by q. Notice I use the hats because we don't have the actual population proportion, because we're trying to estimate it, right? And that's the point of this process. And the other point is that formulas are kind of similar, because instead of standard deviation squared here, I have product of P and Q. And I guess that's what they provide us with in this little section as well. So you can see this formula that appears for the sample size among the exercises right here. And calculating sample size, I believe, is a somewhat nicer procedure, but you always want to round up. Let's recall what this is. I think I just saw an exercise that followed the problem we did, finding the sample size. Actually not. So let me go to the previous problems and locate one. Determining the sample size, like exercise number 21, for example. That gives us error. So I'm looking at problem 21 in the same section. The other kind of questions. So if error is 0.6, people say, why is it a margin of error? Why isn't that just an error? Well, that's the way people usually call error, margin. So it may be no more than that. If it's smaller for the error, it's better, but no more. That's why they use word margin. Then the confidence is favorite 99%. So we right away know they're talking about z-score, right? And we just utilized this in a previous exercise as well. The z was 2.575. You still remember where it came from? Let me double check. Where's my tables for Triola textbook? So first choice in the search will be my tables. And at the end of this, tables with positive z-scores, right? There was a little diagram, and that's where 2,575 that corresponds to 99% is. So let's go back and get another number here. This other number, P and Q, and they are not known. What does that mean? Well, we make our best estimate if P and Q are not known, and the best estimate is the possible closest value. So if P as well as Q supposed to be in the interval from 0 to 1, then the best estimate is always the middle value, or 0.5. So we know it's not 0.5, it may be something else, but that's our best possible estimate. So 50-50 is what we take, and then use the formula and get the sample size. So z 2.575 that I square, then multiplied by P and by Q, so by 0.5, and then by another 0.5 once again, and then divide this by error 0.06. So we got these numbers to plug in the calculator carefully. So let us do this. So I got 2.575 to the second power times 0.5 times another 0.5, and then we divide this by 0.06 squared. So I think it's pretty straightforward, as long as you actually get a calculator and doing it. And that's what last time I asked you to do, and I have a feeling that not lots of people are actually doing it, because if you calculate this along with me, I'm sure you would have no problems plugging numbers in the calculator. So try it, try it. I know it's kind of fun to watch me doing the process because it all looks nice and smooth, but I may miscalculate something, misenter the number. So you really want to make sure that I didn't make a mistake. And to make sure, you just want to double check. So enter it all in the calculator. It is very straightforward if you do this yourself a couple of times. And since I sent you recordings of those lectures, redo the same problems again, and that's pretty much all I can possibly ask you on the tests, to do the same problems. So yes, numbers are a little different, but that's all it is. It looks like not lots of people here today. I know it's end of semester, and I know that it gets already a little bit too much, I understand, but well, this Wednesday, and then we have 2 more weeks to go, and then we'll have a final, so not much time is left anyways. And that's why I would like to move to the something else, because we just keep doing these tedious formulas for confidence intervals. And yes, it's good to be confident and see what is indeed going on, but I'd like to move to probably the most interesting part of statistics story, where we test the hypothesis. And I think that's the key part of statistics class, because you will be able to test any claim whatsoever. So first thing I need to know about the claims is there are three types of claims possible. I think they nicely outlined them someplace here. So here they are. There are three possibilities for the claims. So the first kind I'm gonna do with means. We usually start with means. We used to sample means. So I can say that mean could be greater than zero. Or I can say that mean could be less than zero. Or I could say that mean could be not equal to zero. So those are three possibilities. One is greater, the other is smaller, and the third is not greater, or actually either greater or smaller, so contains both of those. So you could basically claim anything, and of course you don't have to compare it with zero. You can compare with one, or here they compare it with 98.6. It doesn't matter what number we are using, you just want to use some kind of number. And then the process starts of producing the so-called hypothesis. So we put these claims into H1, so-called the alternative hypothesis, because they don't have equal sign. It turns out the zero hypothesis is always going to be opposite and is always going to have the equal sign in it. So, for example, if the opposite of greater is considered, it will be less than or equal. So I put it in the H0. Analogously, the opposite to smaller will be greater, right? So I can say mean is greater than or equal to zero, the opposite. And for the third case, the opposite to not equal will be equal, right? Not equal, the opposite is equal. So we got so-called hypotheses set up for those three different possibilities. So it's always going to be one of these three cases. So what people do is they make pictures on a normal curve, because we're dealing with mu, with mean, of those so-called H1 hypotheses. So H1 is going to be here because it's somewhere on the greater than zero side. So zero is always in the middle. So H1 is on the right side somewhere schematically. Or if you're looking at the second case, when mean is less than zero, well, that'd be on the left side from zero. So someplace so-called left tail will be my H1. So nowadays I always make a picture of H1. That's how it's being established. And then finally, there be so-called two-sided hypothesis because it's either greater or less. So H1 is split into two pieces if we're going with not equal. And that's where this whole process actually starts. And the key part is always put H0 with the equal sign. So today I just don't want to do any particular exercises. I just want to give you an introduction into the story of testing those hypotheses. Because the good thing about that is they're all pretty much same cases. So if you are actually given some type of a statement to put down or claim, people say, then what I can do is produce the claim. So how about if I just look at the exercise number 5 that says mean annual income is greater than 50,000. So somebody says mean is greater than 50,000. People say that's what they claim. Somebody says, no, I totally disagree with that. Okay, you may agree, you may disagree, it may be wrong claim. It doesn't matter to us. All I need is to put it in H1 because it doesn't have the equal sign. And that's the key idea here. So if you don't have equal sign, it's H1. And that's it. How about part 6, exercise number 6? It says mean IQ for statistics students is at least 110. At least means it's not less. Remember, I already had word at least. It could be greater than or equal. Okay. So this is going to be H index 0 because A0 has equal sign. I say, so what? Here's H1, here's H0. What does this really mean? Well, actually, there is always the opposite to H1, which is H0, and always opposite to H0, which is H1. And if you take the opposite of greater, it's going to be less than or equal to, because remember, H index 0 always has equal sign in it. And similarly with the exercise 6, H1 is going to be the opposite to greater, is going to be less than, and there is no equal because it's already taken by the greater. So please notice that your claim could be either in H0 or in H1. To be honest, we don't really care where it is. We just want to make sure you put it in the correct place. And that's about it. So how about another one that says $12. Salaries among the women business analysts have standard deviation greater than 3,000. Is this H0 or H1? What do you think? And the answer is, look at equal sign. Do we have equal sign? No. So it is H1. This is it. So we just need to decide if that's H0 or H1. How about if you tell me for exercise number 11, if that's H0 or H1? They say mean amount of Coke is at least, mean is at least means not less, greater than or equal to 12 ounces. So for today's little quiz, tell me, is this H1 or H0? So that's a question to you. And once you answer it, you can log out and enjoy the rest of the night. I think that will be fair, right? So H0 or H1. All you need to do